is two parts of it. Maybe I just recall those two parts. So if you have a function so if we have a function which is continuous on AB, and we define a new function f of x by using the definite integral, but the upper limit is a variable, then the first part of the fundamental theorem of calculus tells us that this function is an antiderivative of f of t, so the derivative of f is of capital F is equal to small f. Now, so this is the first part. The second part tells us that if f is an antiderivative of small f, then if you are faced with the task of computing the definite integral, there is a very easy way to do this, namely you take the antiderivative and you evaluate it on the upper and lower limit. For this we are going to write frequently f of x, and then we write here a line AB. This is just notation. Okay, so last time we already discussed how to prove those results, and I already explained why those results are important. Now in particular, the second part of the fundamental theorem of calculus gives now a very easy way to compute many integrals, and last time at the end of the lecture I showed you already many examples. Moreover, the second part here also gives you a way now to compute complicated limits, because if you have some limit and you recognize the limit as a Riemann sum, you can actually rewrite it to an integral and use this easy way to evaluate the integral. So for instance, I showed you already last time, an easy example is if someone gives you this limit here, 1 over n plus I, okay, and asks you to compute it, okay. Now, the way we can take is, okay, you recognize that this is the limit, n tends to infinity, 1 over n, sum from I from 1 to n, 1 over 1 plus I over n. And you see this is a Riemann sum. Okay, so you see, okay, I can write this as the integral from 1 to 2 dx over x. Okay, and I know that an antiderivative of 1 over x is given by ln of x. I apply this part, so I have ln of x evaluated at 1 and 2, which gives ln of 2. Okay, so you can reverse this now. This is the important message. Okay, whenever you have to compute such a limit, okay, and you recognize that the limit is a Riemann sum, you can rewrite it to integral, and this gives you a shortcut to compute this limit. Okay, so for instance, I think 2 years ago, in one of my in-class homeworks, I had an example which was a little bit similar to this, but a little bit more tricky. So for instance, the example was, okay, compute this limit. The product, I from 1 to n, 1 plus I over n over 1 over n. Okay, so this doesn't look like a Riemann sum because it's a product. Okay, you all know this sign, right? You all know this sign. The product. This is the product. So this is like the sum, but this is the product. So I take those n numbers and multiply them. Okay, it's the product. So for instance, the product I from 1 to n of I is n factorial. Okay, the product. So this is the product sign. Okay, so this was an in-class homework maybe 2 years ago, but not many students could solve it. Now, the main problem is because here's a product, there's no sum. Okay, so you do not see what is the relation to a Riemann sum. But how do you turn a product into a sum? You write e to the ln, okay, because ln of a product is the sum of the ln's. Okay, so the only idea you need is, okay, you write this e to the. You have a limit, n tends to infinity, e to the ln of this, but the ln becomes a sum. So you have sum I from 1 to n, ln 1 plus I over n, 1 over n. Okay, and this is now indeed the Riemann sum, because you can take down this 1 over n, and you see, okay, this is really a Riemann sum here. Okay, if you can take, of course, the limit into the exponent, because e is a continuous function. So you have this here. Okay, and you see that you can rewrite this now as e to the, and you recognize this is the Riemann sum. This is the integral from 1 to 2 of ln x dx. Okay, and the ln of x, for the ln of x, we know an antiderivative, x times ln of x minus x. So you can use this in order to compute this integral, and that's it. Okay, so you see, you can also compute such limits, okay? Maybe I shouldn't be too lazy, I should compute it. Okay, so this is then e to the x ln x minus x evaluated at 1 and 2, which is e to the 2 ln 2 minus 2 minus, this is 0, so plus 1. Okay, so this one. So you see that if you simplify this, this is 4 over e. Okay, so you see that this limit is 4 over e. Okay, so keep this in mind that you can reverse this now also in order to compute limits. Okay, because we will come back to this next semester. Next semester we will talk about limits of sequences and also series. And you should recall this then next semester, because some of the limits maybe you might be able to use this method to solve them. Okay, so any questions to this? I admit this is a quite tricky example, so because you need this idea that you write it as e to the ln. Okay, if you don't have this idea, you cannot solve it. So it's not a very suitable example maybe for a in-class homework. Okay, so you see already from here, actually from this part. Okay, this part here motivates a new definition, namely since if you compute the definite integral and you get the antiderivative, okay, so it seems to be a good notation to say that to use a new symbol for the antiderivative, namely to use the same symbol but no limits, okay, in order to denote antiderivatives. And this is the so-called indefinite integral. Okay, so the difference between the definite integral is definite integral has lower and upper limit, and is defined as a limit over Riemann sums, and the indefinite integral is by definition, this is actually what you have learned in high school already, is just an antiderivative. Okay, and the reason why I haven't used this notation from the beginning is because this result motivates, okay, to use the integral sign also in order to denote antiderivatives. Okay, so the indefinite integral okay, it's just a notation for an antiderivative. Okay, so if you have a function f of x dx, then if we do not have, so actually they're not really related, okay, because this is a certain limit, but this is just another notation for a function, or maybe even more functions where the derivative of f of x must be equal to f of x. So this is just another symbol for antiderivative, more convenient one. If we use this symbol, we do not have to write that large f is an antiderivative of f. We can just write it like this. Okay, and once more, this notation is clearly motivated by the first part of the fundamental theorem of calculus. Now, also you can use this now in order to rewrite the second part of the fundamental theorem of calculus more conveniently. So in order to compute the integral, what you do is you find an antiderivative. Sorry, you find an antiderivative and you evaluate it at a and b. Okay, so this already tells you now, using this notation, this already tells you now how to do it. Okay, so you first find the antiderivative, and then you evaluate it at upper and lower limit. So it's just for convenience. There's nothing new here. So it's just a more convenient notation for antiderivatives. Normally, most of the time, if we use this symbol, okay, what we want to find are all antiderivatives. Okay, so for instance, if you have the function, let's say ln of x, okay, then we have seen, okay, that because the domain of this function x larger than 0, so all antiderivatives of this function are given by x ln x minus x plus c. Okay, but the situation is a little bit different if f of x is equal to ln absolute value of x. Okay, because now the domain is are all x. So the domain is now all x which are not equal to 0. Okay, so first you have to guess the antiderivative. Now if you guess the antiderivative, you will easily see x ln absolute value of x minus x is an antiderivative of this function here. Okay, but all antiderivatives for all antiderivatives, you have to divide into two cases, namely x is larger than 0 and x is smaller than 0. In this situation, you have x ln x minus x plus some constant, and in this situation, you have x ln minus x plus, and the important thing is another constant. Okay, so if those two, if those two, of course, those two constants might be the same, then you get many antiderivatives, but not all. Okay, all antiderivatives are given by this here, and there are not more. We know this from the mean value theorem. So actually, if you want to find antiderivatives of a function f of x, you first have to make clear what is the domain for you. Okay. If you say the domain of this function f of x are all x larger than 0, but it doesn't make sense, then you don't have to write the absolute value. But in this case, all antiderivatives are given by those functions here. Okay. But if the domain is the largest possible domain, then all antiderivatives, for all antiderivatives, you have to divide into x larger than 0 and x smaller than 0. The reason for this is because we know if the derivative of two functions is the same, the two functions just differ by constant. Okay, but this is if you look at this result, what we have to assume is that both functions both functions are given on an open interval. Okay, but here this is not an open interval; these are two open intervals. So you apply this result, which we have proved previously, to both of the intervals. Okay, for both of the intervals you get a constant, but the constant is not necessarily the same. Okay, so similar, for instance, if you have this function, okay, now of course you could give the answer this one. Okay, so these are indeed antiderivatives of this function, and indeed those are all antiderivatives if the domain of this function is x is larger than 0. Okay, but if you consider as domain all numbers which are not equal to 0, these are not all antiderivatives. Okay, so if you consider, so this would be here domain x is either larger than 0 or smaller than 0. But if you consider as domain if you consider as domain all x which are not equal to 0, then the answer is a little bit different. Then you have minus 1 over x plus c if x is larger than 0, and minus 1 over x plus d if x is smaller than 0. Okay, it depends on the domain, essentially. So in the homework problems, we had one problem of a function where the function, I don't remember the function, but the function was not defined as x is equal to 0. So you have essentially the same situation, and for the answer, you have to tell me. I mean, you can give this answer, okay, it's okay, but you have to tell me what is the domain. Okay, because it depends on the domain. You should recognize that the question to find all underderivatives depend on the domain. I already stressed this before. I know this is something which causes confusion because in high school you are very sloppy and just write plus C all the time. Essentially because you haven't discussed this part in high school, so students tend to, when they come to university, they just tend to do the same. Okay. Now, for those indefinite integrals, of course we already can find quite a lot of indefinite integrals just by reversing the process of differentiation. And you find a table. So, for instance, we know that the integral of the indefinite integral of cosine of x dx is equal to the sine of x plus a constant, and so on and so forth. So the only thing you have to do is you reverse the rules for differentiation. So you also know that the integral of, for instance, 1 over 1 plus x squared dx is the arctangent of x plus a constant, and so on and so forth. And you find a table in our textbook. But so far we haven't, what we essentially will focus on in next few weeks is finding a more systematic way of computing, of finding indefinite integrals. Because so far we can just reverse the rules of differentiation, and this will give us, of course, tools how to find simple laws, how to find simple rules, how to find indefinite integrals, but we will certainly need more. But in particular, for this function here, f of x, okay, apart from guessing, you might guess, okay, is there not a better method to find this function where you don't have to guess? And indeed, there will be one, and we will learn it maybe next week. Now, apart from the indefinite integral you find in our textbook, this I think is chapter, I don't remember, 5.4 maybe, which is called Indefinite Integral and the Net Change Theorem. Now, the net change theorem is a word which I don't know whether other textbooks are using it, but I've never heard it before I read this textbook. So it seems to me that the author has invented it, and actually it's not necessary to call this theorem a new theorem, because essentially this is just the fundamental theorem of calculus, just another name. But so what you essentially want to do is to explain why the author is using another name for the second part of the fundamental theorem of calculus. Now, we saw already that if you have given velocity, so if some particle is moving on a straight line, you have given the velocity function, you are interested in the position function. In this case, we saw that, or the distance traveled. In this case, we saw that, okay, we can approximate, if we are interested in the distance traveled from A to B, we saw that this here gives an approximation, or not only an approximation. So we use the Riemann sum to approximate the distance traveled, and we said, okay, in the limit, what we will get is the distance traveled. Now, I already emphasized that actually in physics, so that this is equal to S of B minus S of A. This is something which the intuition tells us, okay, but mathematically, so maybe for physicists this is a proof already, okay, but so they don't have to prove the fundamental theorem of calculus. It's trivial for them, because here you approximates, you use this way to approximate the distance traveled, and what you should get in the limit is the distance traveled. But in mathematics, it's quite different, because this is something we have defined in terms of limits, some object, okay, and we have to prove that they are actually the same. Okay, I explained this earlier. In mathematics, even also in physics, but in physics they do not care so much about details. Okay, so in mathematics you have to prove this. Okay, and we proved it. Namely, the second part of the fundamental theorem of calculus exactly tells us that this relation is satisfied. Okay. Now, this, strictly speaking, and this is maybe a little bit hard to grasp, and if you read this in the textbook, you might think everything is trivial what the author is telling you. So, strictly speaking, after we have proved the second part of the fundamental theorem of calculus, we get many such relations from physics. Okay. Maybe you might have intuitively used them already before, but actually now they are strictly established. Essentially, what the second part of the fundamental theorem of calculus tells you in physical terms is that the integral of the rate of change is equal to the net change. Okay, and this is the so-called net change, what the author called net change theorem. It's just a reformulation of the second part of the fundamental theorem of calculus. So I'm not going to write down this name, because I don't think it's necessary to give it a different name. But from this you get that you get many laws. So for instance, if the velocity does not necessarily satisfy a larger or equal than 0, then what you get here, okay, if the movement takes place on a straight line, then what you get here is not the distance traveled, but the displacement. Okay, so the displacement. And if you are really interested in the distance traveled, what you have to add is the absolute value. So this will then be the distance traveled. Okay, so let's maybe. This is just 1 minute. Let's do a simple example. So, for instance, if you know that v of t is equal to t squared minus 2t minus 8, and you are interested in the time period from 1 to 6, so if you want to compute the displacement, okay, then you have to compute the integral from 1 to 6 of this function here, t squared minus 2t minus 8 dt. Okay, so you guess an antiderivative. So this is t to the cube over 3 minus t squared minus 8t evaluated at 1 and 6. And if you compute this, then you get minus 10 over 3. But if you want to compute the distance traveled, then you have to look at the absolute value. Okay, and for this you have to look at the function. So you have the integral from 1 to 6. I should mention that the absolute value here does not possess any problem for the definition, because this function is certainly continuous. If v of t is continuous, the absolute value is always continuous, and the composite function is continuous as well. Now you see, okay, that you can this as t minus 4 times t plus 2. Okay, so you see that actually the critical point is 4, so we divide it into two integrals, one from 1 to 4, and the second one from 4 to 6. Now the second one is positive, so we have t squared minus 2t plus 8 dt, whereas the first one, if we drop the absolute value, will be negative, so we have t squared minus 2t plus 8. And the answer, if you do the computations, is trivial. Should be 98 over 3. I'm not clear, I cannot really read it. So 98 over 3. Okay, so this is one example from physics, and you find if you take a look in our textbook, there are many more situations where the what the author called the net change theorem, but you shouldn't be confused by the name. This is just the same as the second part of the fundamental theorem of calculus can be applied. Like you see in our textbook some applications from physics, some application from chemistry, and so on and so forth. But you have encountered them already in other classes, so I'm not going into details and talk more about this. Okay, so but one of our main aims in the sequel is the question how to compute in a systematic manner indefinite integrals. Now we will gradually realize that the task of integration is slightly more complicated than the task of differentiation, and I will explain next time, or maybe next time, what the reason behind this is. I already hinted what the reason behind this is, namely some of the integrals, like this one, we know that this function here, because it's continuous, has an antiderivative. Okay, we know this. We also know how to write down the antiderivative, but the way we can write it down, the antiderivative, is not very pretty. We have to use the integral from 0 to x e to the t squared dt. So maybe not. You maybe would like to have an expression for it. Okay, and for instance, for this integral, it can be proved it's not possible to express it in the functions we know so far. Okay, and this essentially makes the task of already here it should be pretty clear that the task of integration is more complicated than the task of differentiation, because for derivatives, if you have given an expression, you have you apply your rules and you get the derivative. But here the situation can be quite different. So there might be functions which actually have an antiderivative, but it's not easy. You cannot express them in terms of the function which we know. If I say in terms of the function which we know, I include also sine, cosine, and so on. Okay, and also the logarithmic functions, essentially logarithmic functions, exponential functions, trigonometric functions, inverse trigonometric functions, and everything which is polynomial and so on. This is what we know, and there is a theory in mathematics which proves that this cannot be expressed in the functions in terms of functions we know. But this is something you, of course, are not going to learn in this class, because it's much more complicated. But this is just in order to let you understand why the task of integration is more complicated than the task of differentiation. Now, we start with the first rule, which is the so-called substitution rule. This is something maybe you have already applied in high school, or you have already used in other classes. Like let's look at this integral. This integral is pretty different to the integral I showed you before. So if you drop this one, okay, it's not possible to find an expression. But for this one, it's indeed possible. This is another reason why integration is more complicated, because for some integrals, given integrals, it might not be possible to compute them. Okay, for others, it might be possible, and it's since you do not, and it's quite hard to decide actually which one you can express in the given functions and which not. So this makes the task of integration, in particular for students who just start doing it, more complicated. Now, here maybe in high school you have already learned how to solve something like this. So you write y is equal to x squared. So you substitute, you introduce a new variable y. Now this makes sense because the derivative of x squared is essentially this one. So you see that dy is equal to 2x dx. Okay. Now you plug everything in. So you have you replace so x e to the y squared, and you replace dx by 1 over 2x. And now you see, the reason why this works is because this here cancels out. Okay, and what remains is, sorry, it should be y, of course. And what remains is just a function of y. And this one is very easy to integrate because we know that this function, the derivative is itself. So you have 1/2 e to the y plus a constant. And then you replace y again by x squared. Actually, this is something which we could have guessed also from this function if you are asked to find the antiderivative. Now, of course, this reason is completely wrong, okay? Because this does not make sense here, okay? Because actually what we mean is that dy over dx is equal to 2x, and this is not a fraction, so we are not allowed to write this like this. Okay, so this is kind of not really correct. And also to plug this into this dx doesn't make any sense because this is a symbol. This is together, okay? This dx doesn't have any sense. Doesn't make any sense, okay? We just write everything like this. So this is just notation, okay? But still, this somehow works, okay? Which is quite surprising. Now. But still, if we want to use something like, if we want to use this kind of reasoning, we have to prove it. Okay, so we should give a strict proof of it. Now, you might already realize the substitution rule somehow is reversing the chain rule. Okay, so actually, what we want to look at is, or what we have given is something like this here, something which might come out from the chain rule, okay? Because you see already that you have in this function you have plugged in x squared, and the derivative of x squared is more or less there is a multiplicative factor. So actually, what we wanna do is we wanna find such integrals here. Okay. Now, if we assume that f has an antiderivative, so assume that f has an antiderivative. Let's call it capital F. Then you see that, okay, so if you look at this function here and you differentiate it, okay, then what you get is by the chain rule. That's what I mean. The substitution rule is somehow the inverse of the chain rule, this one. Okay, and because this is an antiderivative, so this is equal to plus a constant. Okay. So now this is one way to compute this integral. Another way would be as follows. Okay, so you see that if we switch the variable to u, so we know that this here, because the meaning of this is an antiderivative of small f, which I just said is f of u plus a constant. And if we say, okay, u is g of x, then we can rewrite this to f of g of x plus c. Okay, and the answers are the same. So this means that those two integrals are the same. Okay, so what this means is that the integral f of g of x, derivative of g of x dx is equal to the integral of f of u du, where u is equal to g of x. And this is the same as this here, okay? It's just written differently. Okay, so now you see that Okay, because we realized that those two integrals are the same if the meaning of u is that u is equal to g of x. So we can think about it. We first set u is equal to g of x. Then we plug in here. Then because du is equal to the derivative of g of x dx, and this is and so the du is equal to this. So we can really use this kind of to memorize the rule. Okay, this is not really the method. This is just to memorize the rule, and it's more convenient because it's more intuitive. Okay, so we will every time we use this here. Okay, because it's more convenient to memorize. But you should keep in mind that this kind of way of reasoning is, of course, is wrong. But it's a good way to memorize the substitution rule. So maybe let's formalize the substitution rule. So what do I need? I certainly need that g is differentiable, and I need that small f has an antiderivative. Then this reasoning is okay. Then this reasoning is justified. Okay, so I need some assumptions. So I assume that g of x is differentiable. So this I certainly have to assume because I want to consider this integral. Now, and the range of g of x is an interval. Okay, so moreover, I assume that f is continuous. So let's say this is I here, some interval on I. Okay, so why do I need that? So if I assume that g of x is the range of g of x is an interval and f is continuous on I, then because f is continuous on I, so f will have an antiderivative, and everything matches. Okay. So the reason why f, I explained it already last time. So like from the first part of the fundamental theorem of calculus, as a consequence, we get that every continuous function on an interval has an antiderivative. Okay. So this here is just a more complicated way to write f has an antiderivative. Okay, but it's easier to justify. Then, so if this is justified, then if this is satisfied, then I have that the integral of, f of g of x, derivative of g of x dx is equal to integral f of u du, where u is equal to g of x. Okay. So this is the substitution rule. And just once more, so from the proof you see already that the substitution rule is kind of the inverse of the chain rule. Of course, this will be our general approach in order to find integration rules. Of course, we are going to try to invert the rules for differentiation. Because from the fundamental theorem of calculus, we know that integration and differentiation are inverse processes. Okay, so maybe let's look into some examples. Or are there any questions? Okay, so now, for instance, some very easy examples. Okay, so for instance, this one. So the only thing you have to realize is that 1 over 1 plus x squared is just the derivative of arctangent of x. So what you're going to do is you substitute u to be the arctangent of x. Then du is equal to 1 over 1 plus x squared dx. Okay, so this becomes the integral over u du. And this can be easily solved. And now you just plug in your substitution. Okay, this is the answer. Okay, so this was easy enough. So let's maybe look at some is more. Here's another one which is also easy but important. Tangent of x. Also, this falls into this category because you can write the tangent as sine over cosine. And you see that the derivative of cosine is more or less the sine. So the method you're going to take here is you substitute u to be the cosine of x. Then du is equal to minus sine of x dx. So what you get is that this is minus integral du over u. So this is then the minus ln absolute value of u plus a constant. And if we again replace u by cosine of x, what you get is ln of the absolute value of secant of x plus a constant. So you can assume that this is one of the for integration. Okay, the more integrals you compute, the more you know. Okay, so you now can assume you can assume. Okay, this is also now one of the standard integrals for u. And in fact, in our textbook, there is at the end you find a table of the most important or most common integrals. And if you go to the library, you find whole textbooks where you find many integrals. So the more you know, the easier it gets. Okay, because then you can relate new problems to maybe problems you have already tackled. Sometimes it's slightly more complicated to find the substitution. Actually, some of the substitutions are really tricky. We will learn later on more tricky substitutions. This one is not really tricky, but maybe also not so apparent for beginners. Okay, so if you have x to the 5, so the only thing you have to discover is that okay, you can write this as x to the 4 times x. Okay, and if you do now the substitution, u is equal to 1 plus x squared, you have more or less the inner derivative here. And you can replace this here also by the function u. This is important. That's why you can do this. So you see that du is equal to 2x dx. And you see that from here that x squared is equal to 1 minus u. So if you plug this everything in, then you have the integral square root of u. Now here what you get is 1 minus u square, and dx is replaced by 1 over 2 x du, so this one cancels out as it's supposed to be, du. And this here, easy to compute, okay? Because here you just expand it, and then you do term by term integration. So you have maybe once I do this, so u to the 1/2. Then you have minus 2u to the 3/2 plus u squared, so plus u to the 5/2 du. And you just use now the rule that the integral x to the n dx is equal to x to the n plus 1 over n plus 1 plus a constant. And this is only true if n is not equal to minus 1. Minus 1 is the only troublemaker here in this formula. Okay, and you apply this here for every part, and you get the result. Okay, so you see, here maybe it's slightly more tricky to find the substitution, but not really complicated. Maybe, because we just mentioned this example, here's another one, which tells you that sometimes it can be easier to do substitution instead of computations. Okay, so this is an example where actually you do not have to do any substitution. You could expand this here, okay, expand the numerator, and then use term-by-term integration of every term using this formula. But maybe it's more easy to. This should be x. Sorry. Okay, so once more you can expand the numerator. Okay, then you can use term-by-term integration, and by using this formula here, it would be one way. But since here you have to the 8, so maybe too many terms, it's more easier to realize that the derivative of square root of x is more or less 1 over square root of x, 1 over 2 square root of x. Okay, so here it makes sense to do this substitution, okay, because the derivative is more or less as a multiplicative factor in the integrand. So du will be 1 over 2 square root of x dx. Okay, so what you have is that this is 2 times the integral, and then u to the 8 du. Okay, and then this will give you 2 times u to the 9 over 9 plus a constant, and if you replace this again by the substitution, then you get this solution here. Okay, so that you see this is much easier than expanding. For instance, if you have here 1000, you can use the same, okay? And do not expand it, okay? It will take too much time. Okay, so this is another, maybe I should replace this again. This is another example. Sometimes, actually, you have many choices for doing the substitution, and many different choices might all work. Okay, so for instance, for this one, you have many possibilities, okay, for doing substitution. For instance, a substitution which certainly works is sine of x to the cube, because you realize that the derivative of this function is the cosine of x to the cube times 2x, okay, which is more or less a constant, okay, of the which is more or less the remaining part. So if you use this substitution, what you get is the integral. Now you have u, and the rest is 1/2 du. So this gets very easy then. Okay, so you have that this is equal to sine x, or maybe I should do it. Okay, so you have u squared over 4 plus a constant, which is equal to, and then you just replace again u squared by our substitution. Okay, so this would be one way to substitute, but of course it also works if you substitute. It also works if you use the substitution cosine of x to the cube. Okay, because also this here is more or less the derivative of this function, so you have du is equal to minus sine x to the cube. This is completely wrong, sorry. You didn't tell me. Okay, but it's similar, so the original integral is equal to minus 1 over 3, and you have the same integral of u du, which is minus u squared over 6 plus a constant. And if you again plug in our substitution, okay, those two answers are not different; they are the same. Okay. Also, they might look, if you do not look very carefully, they might look different. Okay, but they are the same because sine square plus cosine square is equal to 1. So the difference is in the constant here. Okay, so if you take out here from the constant of 1, the rest is another constant, then you can rewrite this solution to this solution. So they are the same. Okay, but of course another substitution. Any questions? Any question? Yes or no? Any mistake? No? This one? Here, you mean this? I'm missing this here? Yeah, thanks a lot. Okay, so of course I forgot to write this, sorry. Okay, but the essential thing is those two solutions are the same. And you see that another substitution, so this would be one substitution, this is one substitution. Another substitution which would work as well is u is equal to x to the cube. Okay, also this substitution would give you the answer. Okay, so if you use u is equal to x to the cube, then what you get is du is equal to 3x squared dx. Now, our integral becomes 1 over 3, the integral, and you have here sine of u, cosine of u, du. Okay, and you can rewrite this as 1 over 6, the integral, and then you have sine 2u du. Okay, now you can do another substitution. And then you plug in everything and you get the final result. Okay, so, but essentially from here is easy because you choose minus cosine of 2u over 2. Okay, so this will be another derivative of this one, and then you get the solution. And then you plug in the original one. Okay, so in some cases you have many different ways to substitute. Okay, and every substitution might work. In our textbook, you find some other examples where you have also a couple of different ways of finding a substitution. And for more these are all easy examples, but for more complicated examples, sometimes it might be quite complicated to find the tricky substitution which will reduce your given integral to something which is simple. Because this is essentially the task of the substitution rule. Now, so this was for indefinite integrals. For definite integrals, actually, of course, you can use the same reasons. So, for instance, if you have x e to the x squared dx, because the indefinite integral, you anyway have to first compute the definite integral, the indefinite integral, and then to evaluate it at the two limits, upper and lower limit. Now we found already that, okay, this integral is e to the x squared half, evaluated at 1 and 2. So what you see is that this is 1/2, and then you have e to the 4 minus e. Okay, so this is one way how to apply the substitution rule for indefinite integrals. Another way which would be you also when you do the substitution, okay, you also change upper and lower limit. So we have also a substitution rule for indefinite integrals. So this is another one, but for indefinite integrals, so the assumptions are a little bit different. So assume that f is g is the derivative of g exists and is continuous on AB. And f is continuous on the range of g. Then if you want to compute the integral a to the b f of g of x, derivative of g of x dx, okay, you can, using our standard transformation, you can transform this to f of u du, And now the only thing you have to do is you have to replace also the upper and lower limit by g of a and g of b. But the rule in order to memorize this is just the same. So you replace u is equal to g of x. Now you transform upper and lower limit. Okay, and then you plug in for g of x u, and this here is getting du. Okay, so this is a little bit different from this one, okay, from this method. So this is actually, we have to prove it, but the proof is trivial. Maybe I should point out the assumptions. You see that the assumptions are a little bit different from the version for indefinite integrals. You see that one difference is that I assume that the g is not only differentiable, but also that the derivative is continuous. Why do I need that? Who sees why do I need this assumption? If you look at the first version, I just assumed that the derivative of g exists, but now I even assume that the derivative must be continuous. Why do I need this assumption here? It's very easy because otherwise, if the whole function here is not continuous, the integral is not defined. Okay, so I need that this part here is continuous. Okay, also this part must be continuous, then everything is continuous. So I will assume that this is continuous, and I need that f is continuous on the range of g because f must have, for the proof, f must have antiderivative. You do not really see this here, but we need here for the proof that f must have an antiderivative. Actually, we just have proved that a function which is continuous on an interval has an antiderivative. So here there is actually something, because this is the formulation from the textbook, there is something contained in the formulation which we have not proved, but which is true, namely, if you have a continuous function on an interval ab, the range will again be an interval for a continuous function. This is something which follows, of course, from the this is more or less the intermediate value theorem, and this is what we need here as well for the assumptions. But the proof actually is very easy. Again, we because of this assumption, small f has an antiderivative. Call it capital F, and f of g of x is then an antiderivative of f of g of x times derivative of g of x. So you see that by the fundamental theorem of calculus, the left-hand side, is equal to f of g of b minus f of g of h, where the right-hand side, so this is the left-hand side, where the right-hand side, if you look at this one, so capital F is the antiderivative of this one, is also f of g of b minus f of g of a. And because they are the same, those integrals are the same. Okay, so it's trivial. Okay, so there shouldn't be a problem here. So actually for the substitution rule, if you apply the substitution rule for definite integrals, there are two different ways to apply it. The first way would be, okay, you first find of this function an antiderivative and then evaluate it at the upper and lower limit. Or the second way is when doing the substitution, you also replace upper and lower limit by new bounds. And then for the rest, you do not have to. So the advantage maybe you have here is that now you just have to, you do not have to substitute back. Okay, you just use those new bounds in order to compute the integral. This one. If you look at this example here, the first thing you notice, because of the area interpretation of the integral, okay, if you look at this function, okay, if you plot this function is roughly okay, has a maximum at x is equal to 0 and tends to 0 if x is getting large and small. Okay, and so because you have here a maximum, okay, so this here computes the area, so it certainly must be larger than 0. This is something we easily observe. Okay, now observe this. So let's write this as x to the minus 4 over 1 plus x to the minus 4 dx, and use the substitution u is equal to x to the minus 4. Okay, so you see that du is equal to minus 4 x to the minus 5 dx. So in particular, because the dx is equal to minus 1 over 4 x to the 5 du, but from here you can you easily observe that x is equal to u to the minus 1 over 4. So this is minus 1 over 4 x to the u to the minus 5 over 4 du. Okay, so the integrand becomes. It's not good. So maybe I can erase this here because this is the only important thing here. So this is our substitution. Maybe I write the substitution once more here. Okay, so you see that this becomes the integral. Now you have here u over 1 plus u. Okay, and here you have minus 1 over 4 and u to the minus 5 over 4 du. And for a lower and upper limit, if you plug it in, you get 1, 1. Okay, so it's equal to 0, which is not possible because the area is positive. Okay, so where is the mistake? You see, because the integral is from 1 to 1, it must be equal to 0. Okay, but from the area interpretation of this one, you see there is an area which is larger than 0. Okay, so where is the mistake? What do you think? Where is the mistake? Hmm? I don't need to use the antiderivative because the boundaries are getting simpler. So there shouldn't be a problem in rewriting it like this here. It's okay. So who can explain us where the mistake is? Or can you explain this in more details? Maybe what do you mean by the antiderivative? Maybe the most easiest reason you should find is, okay, why am I not allowed to apply this theorem? If I'm not allowed to apply a theorem, normally the assumptions are not satisfied. Okay, so you just have to tell me which assumption is not satisfied. So who knows it now? That's why I kept this here, okay, because you can look at this result here and you just have to tell me which assumptions are violated. Yeah, right. Because this is actually the function which you substitute, and this function not differentiable, not even differentiable. Okay. Of course, the derivative not continuous, but not even differentiable. Okay. So that's why you are not allowed to use this. So you have to be careful sometimes when using the substitution rule. Because sometimes this can be quite tricky sometimes. Sometimes the integrand is somewhere not defined, but not easy to see. Okay, so sometimes this is quite often that this is overlooked, and what you get then is something which is actually the wrong result. Okay, so any questions? Now this is almost finished. What I will do on next Monday is now we are finally ready to define precisely the logarithmic functions and exponential functions. This is something I have explained in the first lecture. That in the first lecture I tried to define a to the x, but we haven't been very successful in the first chapter in order to define this function. In particular, a to the x, if x is an irrational number, we just looked at the graph and filled holes, okay, something which is not very precise. And I told you in the first lecture that we will, once we have learned the tools on integration, we will be able to give a precise definition of the logarithmic functions. So as a preparation for next time, Monday, you should forget that what you know about logarithm and exponential functions. This will be quite helpful, you know. So on Monday, we will take the point of view that we have never defined the logarithm, never defined the exponential function, and wanna, for the first time, try to find a precise definition. Now, our textbook is more special because it uses those functions from the beginning, but there are quite a lot of textbooks on calculus which use the logarithmic functions and trigonometric functions just after they have discussed the fundamental theorem of calculus. So no examples in all the chapters before. Do not use those functions because this is actually now the right time, and this is for the first time that we can really give a precise definition of the logarithmic and exponential functions. And this is what we are going to do next time.